Alright, here's the second part. We proved this result about if something converges uniformly, then the limit of the integrals equals the integral of the limit f. And why do we need uniform continuity? Well, I mean, certainly it works because I gave you proof with uniform continuity, but the basic idea is if you look at something that converges, I want the other one. If you look at something that converges uniformly, say right here, now I'm looking at a bunch of f sub n. All of these f sub n's are all close, the area underneath these are all close to the area underneath the x squared limit here. The limit happens to be x squared. So since every point of the function is always close to x squared, that's the uniform part, is that it gets close kind of at the same time. That means that the area is going to be close too. Let's contrast that with a pointwise example that we've seen before. Again, the limit's going to be x squared. In fact, it's going to x squared more smoothly over here. But notice here, you always have this big loop here. This big loop has a lot of area underneath it. So since I'm going pointwise to x squared, and it will converge pointwise to x squared. But this big loop of area is going to throw off the integrals, so the limit of the integrals might not be equal to the integral of the limits. So let me give you a very specific example. So a very specific example is my f sub n are going to look like, how about on the interval 0 to 1, at 1 over n, I'm going to have a value of n. Maybe like so. And then for the rest of the time, I'm going to have value. In fact, let's even change colors. So the graph will be green. The rest of the time, I'm going to have value 0. Now, as n goes to infinity, the 0 is going to get more and more. In fact, actually, I have to make one small adjustment. I screwed up this a little bit. I need to make, oops, I need to start writing again. Here we go, now I'm ready. I'm going to make this value 0. Because then, notice that this part is going to get smaller and smaller, so the entire thing is going to converge to 0. So I know that these f sub n's are going to converge to 0 pointwise. But notice that the area, the integral, so the integral of f sub n is always going to be equal to 1. Because you always get 1 over n times n. This rectangle is always going to give you an area of 1, and that's always going to give you a rectangle of 0. But the integral of the limit is always going to equal the integral of 0, which equals 0. So if you take the limit of these, right, the limit of the integral of, from 0 to 1, of f sub n, that's just equal to the limit of the sequence 1, which is clearly 1, which is not equal to 0, which equals the integral of 0, which equals the integral of f. So what goes wrong with pointwise? Pointwise, or uniform, everything kind of has roughly the same area, but pointwise, you can have these big loops that go way off, and that can cause the integrals to be huge, relatively speaking. So that's what goes wrong with pointwise. Bye-bye.